Chapter 1, Earth Systems. Introduction. Earth is sometimes called the water planet or the blue planet because azure seas cover more than 2/3 of its surface. Earth is the only planet or moon in the solar system in which water falls from clouds as rain, runs across the land's surface, and collects in extensive oceans. It is also the only body we know of that supports life. The Earth's four spheres. Imagine walking along a sandy beach as a storm blows in from the sea. Wind whips the ocean into whitecaps, while large waves crash onto shore. Blowing sand stings your eyes as gulls overhead frantically beat their wings en route to finding shelter. In minutes, blowing spray has soaked your clothes. A hard rain begins as you hurry back to your vehicle. During this adventure, you have experienced the four major spheres of Earth. The beach sand underfoot is the surface of the geosphere, or the solid Earth. The rain and sea are parts of the hydrosphere, the watery part of our planet. The blowing wind belongs to the atmosphere. Finally, you, the gulls, the beach grasses, and all other forms of life in the sea, on land, and in the air are parts of the biosphere, the realm of organisms. You can readily observe that the atmosphere is in motion, because clouds drift across the sky and wind blows against your face. In the biosphere, animals, and to a lesser extent plants, also move. Flowing streams, crashing waves, and falling rain are all familiar examples of motion in the hydrosphere. Although it is less apparent on a day-to-day basis, the geosphere is also moving and dynamic. Vast masses of solid rock flow very slowly within the planet's interior. Continents move, while intervening ocean basins slowly open, then collapse. Mountains rise and then erode into sediment. Throughout this book, we will study many of these phenomena to learn which energy forces set matter in motion and how these motions affect the planet on which we live. Figure 1.1 shows schematically all the possible interactions among the spheres. Figure 1.2 shows that the geosphere is by far the largest of the four spheres. The Earth's radius is about 6,400 kilometers, roughly the same distance as Miami to Anchorage. Despite this great size, nearly all of our direct contact with Earth occurs at or very near its surface. The deepest well penetrates little more than 12 kilometers, less than 0.2% of the distance to Earth's center. The oceans make up most of the hydrosphere, and although it can extend as deep as 11 kilometers, the ocean floor averages only about 4 kilometers in depth. Most of Earth's atmosphere lies within 30 kilometers of the surface, and the biosphere is a thin shell about 15 kilometers thick. The geosphere, our solar system, coalesced from a frigid cloud of dust and gas rotating slowly in space. The sun formed as gravity pulled material toward the swirling center. At the same time, rotational forces spun material in the outer cloud into a thin disk. Eventually, small grains of matter within the disk stuck together to form fist-sized masses. These planetary seeds then accreted to form rocky clumps, which grew to form larger bodies, called planetesimals, 100 to 1,000 kilometers in diameter. Finally, the planetesimals consolidated to form the planets. This process was completed about 4.6 billion years ago. As the Earth coalesced, gravity caused the rocky chunks and planetesimals to accelerate so that they slam together at high speeds. Particles heat up when they collide, so the early Earth warmed as it formed. Later, asteroids, comets, and more planetesimals crashed into the surface, generating additional heat. At the same time, radioactive decay heated the Earth's interior. These three processes caused the early Earth to become so hot that much of the planet melted as it formed. Within the molten Earth, the denser materials sunk toward the center, while the less dense materials floated toward the top, creating a layered structure. Today, the geosphere consists of three major layers: a dense metallic core, a less dense rocky mantle, and an even less dense surface crust. The temperature of modern Earth increases with depth. At its center, Earth is 6,000 degrees Celsius, as hot as the sun's surface. The core is composed mainly of iron and nickel. The outer core is molten metal. However, the inner core, although hotter yet, is solid because the great pressure compresses the metal to a solid state. The mantle surrounds the core and lies beneath the crust. The physical characteristics of the mantle vary with depth. From its upper surface to a depth of about 100 kilometers, the outermost mantle is relatively cool, strong, and hard. However, below a depth of 100 kilometers, rock making up the mantle is so hot that it is weak, soft, plastic, and flows slowly, like cold honey. Even deeper in the mantle, pressure overwhelms temperature, and the rock becomes strong again. The crust is the outermost layer of rock extending from the ground surface or bottom of the ocean to the top of the mantle. The crust ranges from as little as 4 kilometers thick beneath the oceans to as much as 75 kilometers thick beneath the continents. Even a casual observer sees that the crust includes many different rock types. Some are soft, others hard, and they come in many colors, as you can see in Figure 1.3. The relatively cool, hard, and strong rock of the uppermost mantle is similar to that of the crust. Together these layers make up the lithosphere, which averages about 100 kilometers thick. According to the theory of plate tectonics, developed in the 1960s, the lithosphere is divided into 7 major and 8 smaller segments called tectonic plates. These tectonic plates float on the relatively hot, weak, plastic mantle rock beneath and move horizontally with respect to each other. For example, North and South America are currently moving west relative to Eurasia and Africa about as fast as your fingernails grow. These continental movements are causing the Atlantic Ocean to grow larger and the Pacific Ocean to shrink. In a few 100 million years, almost incomprehensibly long on a human time scale but brief when compared with planetary history, Asia and North America may collide, completely collapsing the Pacific Ocean and crumpling the leading edges of the continents together into a giant mountain range. In later chapters, we will learn how the theory of plate tectonics explains earthquakes, volcanic eruptions, and the formation of mountain ranges, as well as many other processes and events that have created our modern Earth and its environment. Scientific awareness, much less scientific understanding, of plate tectonics did not occur until after World War II, and it was not widely accepted among scientists until the late 1960s. Since then, advances in modern technology have accelerated, and so have the tools available for scientists to probe Earth's interior and study its dynamics. Similarly, accelerating computational capacity and new tools are constantly being developed and deployed to explore Earth's oceans and atmosphere. In aggregate, these new tools have generated immense volume of new data available for scientific exploration of Earth's systems. Electronic accessibility to peer-reviewed scientific publications describing the results and analysis of that scientific exploration broadens the global community of scientists and educated non-scientists alike. All in all, it is a marvelous time to study Earth sciences. Earth is dynamic, and we are just beginning to appreciate how much so that is. The hydrosphere includes all of Earth's water, which circulates among oceans, continents, glaciers, and the atmosphere. Figure 1.5 shows the proportion of water in each of these areas. Oceans cover 71% of Earth and contain 97.5% of its water. Ocean currents transport heat across vast distances, altering global climate. About 1.8% of Earth's water is frozen in glaciers. Although glaciers cover about 10% of Earth's land surface today, they covered much greater portions of the globe as recently as 18,000 years ago. During this glacial period, nearly all of Canada, the British Isles, and Scandinavia were covered with ice that was locally up to 4 kilometers thick. In North America, the ice was so massive that it caused the underlying lithosphere to sag beneath its weight. Hudson Bay in Canada exists because the glacial ice melted faster than the lithosphere was able to bounce back. Today, parts of the Hudson's Bay region are undergoing over 10 centimeters of uplift per year as the lithosphere continues to recover from the weight of the ice. As shown on Figure 1.6, upward velocity rates of the ground surface decrease south of Hudson Bay to 0 in the Great Lakes region. South of the Great Lakes, the ground surface is slowly subsiding downward. The boundary between upward rebounding and slowly subsiding regions corresponds very roughly to the maximum advance of continental glaciers during the last glacial maximum about 18,000 years ago. Only about 0.64% of Earth's total water exists on the continents as a liquid. Although this is a small proportion, fresh water is essential to life on Earth. Lakes, rivers, and clear, sparkling streams are the most visible reservoirs of continental water, but they constitute only 0.01% of Earth's water. In contrast, groundwater, which occurs in pores, spaces within soil and rock of the upper few kilometers of the geosphere, is much more voluminous and accounts for 0.63% of Earth's water. Only a minuscule amount of water, 0.001%, exists in the atmosphere, but because it is so mobile, this atmospheric water profoundly affects both the weather and the climate of our planet. The atmosphere is a mixture of gases, mostly nitrogen and oxygen, with smaller amounts of argon, carbon dioxide, and other gases. It is held to Earth by gravity and thins rapidly with altitude. 99% is concentrated in the first 30 kilometers, but traces of atmospheric gas occur as far as 10,000 kilometers above Earth's surface. The atmosphere supports life, because animals need oxygen and plants need both carbon dioxide and oxygen. In addition, the atmosphere supports life indirectly by regulating climate. Air serves as both a blanket and a filter, retaining heat at night and shielding us from direct solar radiation during the day. Wind transports heat from the equator toward the poles, cooling equatorial regions and warming temperate and polar zones. The biosphere is the zone that life inhabits. It includes the uppermost geosphere, the hydrosphere, and the lower parts of the atmosphere. Sea life concentrates near the surface, where sunlight is available. Plants also grow on Earth's surface, with roots penetrating a few meters into the soil. Animals live on the surface, fly a kilometer or two above it, or burrow a few meters underground. Large populations of bacteria live under glacial ice and in rock to depths of as great as 4 kilometers. Some organisms live on the ocean floor, including entire thriving ecosystems based off mineral-rich, superheated water spewing from vents along the mid-ocean ridges. A few wind-blown microorganisms drift at heights of 10 kilometers or more. Despite these extremes, the biosphere is a very thin layer at Earth's surface. Plants and animals are clearly affected by Earth's environment. Organisms breathe air, require water, and thrive in a relatively narrow temperature range. Terrestrial organisms ultimately depend on soil, which is part of the geosphere. But plants and animals also alter the atmosphere through respiration and contribute organic matter to the geosphere when they die. Earth systems. A system is any assemblage or combination of interacting components that forms a complex whole. For example, the human body is a system composed of bones, nerves, muscles, and a variety of specialized organs. Each organ is discrete, yet all the organs interact to produce a living human. For example, blood nurtures the stomach, and the stomach helps provide energy to maintain the blood. Systems are driven by the flow of matter and energy. Thus, a person ingests food, which contains both matter and chemical energy, and inhales oxygen. Waste products are released through urine, feces, sweat, and exhaled breath. Some energy is used for respiration and motion, and the remainder is released as heat or stored as fat. A single system may be composed of many smaller ones. For instance, the human body contains hundreds of millions of bacteria, each of which is its own system. Many of these bacteria are essential to the functioning of human metabolic processes such as digestion. In addition, humans are part of their local ecosystem, which is defined as a complex community of organisms and their environment functioning as an ecological unit in nature. Therefore, to understand the human body system, we must study smaller systems that exist within the body, while also exploring how humans interact with their larger ecosystems. But we're not finished yet. Individual ecosystems interact with climate systems, ocean currents, and other Earth systems. Thus, the size of systems varies dramatically. Large systems contain numerous smaller systems. Systems interact with one another in complex ways. As we have learned, Earth is composed of 4 major systems: geosphere, hydrosphere, atmosphere, and biosphere. Each of these large systems is subdivided into a great many interacting smaller ones. For example, a single volcanic eruption is part of a system. Energy from deep within Earth melts rock, forming magma. Some of this magma escapes during the eruption, along with volcanic gases that react chemically with surface materials. But this volcanic eruption is driven by the distribution and movement of heat within Earth's interior, which is also a system. Volcanic ash and certain gases spewed skyward during the eruption can affect local weather and cool Earth's climate, thereby becoming part of these systems. Heat from the eruption can also rapidly melt glaciers growing near the summit of the volcano, affecting the local hydrologic system. In this book, we will study systems of all sizes and illustrate many of the complex interactions among them. Earth's surface systems, the atmosphere, hydrosphere, and biosphere, are ultimately powered by the sun. Wind is powered by uneven solar heating of the atmosphere, ocean waves are driven by the wind, and ocean currents move in response to wind or differences in water temperature or density. Luckily for us, Earth receives a continuous influx of solar energy, and it will continue to receive this energy for another 5 billion years or so. In contrast, Earth's interior is powered by the decay of radioactive elements and by residual heat from the primordial coalescence of the planet. We will discuss these sources of heat in later chapters. Fundamental to our study of Earth systems are several energy and material cycles. A cycle is a sequential process or phenomenon that returns to its beginning and then repeats itself over and over. During the course of these cycles, matter and energy both are always conserved. They never simply disappear, although either may continuously change form. For example, water evaporates from the ocean into the atmosphere, falls to Earth as rain or snow, and eventually flows back to the oceans. Ultraviolet radiation that we cannot see enters Earth's atmosphere from the sun and heats up the surface, which in turn emits heat. In this book, we will examine the rock cycle, the hydrologic cycle or water cycle, the carbon cycle, and the nitrogen cycle. We will also explore the critical role that energy and transformations of energy from one form to another play in Earth's oceans and atmospheric processes. Because matter exists in so many different chemical and physical forms, most materials occur in all 4 of Earth's major spheres: geosphere, hydrosphere, atmosphere, and biosphere. Water, for example, is chemically bound into clays and other minerals as a component of the geosphere. It is the primary constituent of the hydrosphere and exists in the atmosphere as vapor and clouds. Water is also an essential part of all living organisms. Salt is another example. Thick layers of salt occur as chemical sedimentary rocks. Large quantities of salt are dissolved in the oceans, salt aerosols are suspended in the atmosphere, and salt is an essential component of life. As we can see, all the spheres continuously exchange matter and energy. In our study of Earth systems, we categorize the 4 separate spheres and numerous material cycles independently, but we also recognize that Earth materials and processes are all part of one integrated system. Time and rates of change in earth science. James Hutton was a gentleman farmer who lived in Scotland in the late 1700s. Although trained as a physician, he never practiced medicine and instead turned to geology. Hutton observed that a certain type of rock, called sandstone, is composed of sand grains cemented together. He also noted that rocks in the Scottish Highlands slowly decompose into sand and that streams carry sand into the lowlands. He inferred that sandstone is composed of sand grains that originated from the erosion of ancient cliffs and mountains. Hutton tried to deduce how much time was required to form a thick bed of sandstone. He studied sand grains slowly breaking away from rock outcrops. He watched sand bouncing down stream beds. Finally, he traveled to beaches and river deltas where sand was accumulating. By estimating the time needed for thick layers of sand to accumulate on beaches, Hutton concluded that sandstone must be much older than human history. Hutton had no way of measuring the magnitude of geologic time. However, modern geologists have learned that certain radioactive materials in rocks can be used as clocks to record the passage of time. Using these clocks and other clues embedded in Earth's crust, in the Moon, and in meteorites fallen from the solar system, geologists estimate that Earth formed 4.6 billion years ago. The primordial Earth was vastly different from our modern world. There was no crust as we know it today, there were no oceans, and the diffuse atmosphere was entirely different from the modern one. There were no living organisms. No one knows exactly when or how the first living organisms evolved, but we know that life existed at least as early as 3.8 billion years ago, 800 million years after the planet formed. For the following 3.3 billion years, life evolved slowly, and although some multicellular organisms developed, most of the biosphere consisted of single-celled organisms. Organisms rapidly became more complex, abundant, and varied about 542 million years ago. The dinosaurs flourished between 225 million and 65 million years ago. Homo sapiens and our direct ancestors have been on Earth for 5 to 7 million years, or roughly only 0.1% of the planet's history. In his book Basin and Range, John McPhee offers a metaphor for the magnitude of geologic time. If the history of Earth were represented by the Old English measure of a yard, the distance from the king's nose to the end of his outstretched hand, all of human history could be erased by a single stroke of a file on his middle fingernail. Figure 1.7 summarizes Earth history in graphical form. Geologists routinely talk about events that occurred millions or even billions of years ago. For example, about 1.7 billion years ago, the granite now forming Mount Rushmore cooled from a melt and crystallized. About 500 million years ago, the Appalachian Mountains began to form from tectonic crumbling of the eastern part of the North American plate. About 150 million years ago, a blanket of mud containing the remains of tiny plankton accumulated in deep water off the west coast of North America. That sediment has since hardened to sedimentary rock that was subsequently added to the westernmost edge of North America by tectonic plate motions and today forms the bedrock on which the northern end of the Golden Gate Bridge rests. There are two significant consequences of the vast span of geologic time. 1. Events that occur slowly become significant. If a continent moves a few centimeters a year, the movement makes no noticeable alteration of Earth systems over decades or centuries. But over hundreds of millions of years, the effects are significant. 2. Improbable events occur regularly. The chances are great that a large meteorite won't crash into Earth tomorrow, or next year, or during the next century. But during the past 500 million years, several catastrophic impacts have occurred, and they will probably occur sometime in the future. James Hutton deduced that sandstone forms when rocks slowly decompose to sand. The sand is transported to lowland regions, and the grains cement together. This process occurs step by step, over many years. Hutton's conclusions led him to formulate the principles now known as gradualism and uniformitarianism. The principle of gradualism states that geologic change occurs over long periods of time, by a sequence of almost imperceptible events. Uniformitarianism stipulates that geologic processes operating today also operated in the past. Thus, scientists can explain events that occurred in the past by observing slow changes occurring today. Sometimes this idea is summarized in the statement, "The present is the key to the past." However, not all geologic change is gradual. William Whewell, a geologist in the 19th century, argued that geologic change was sometimes rapid. He wrote that the geologic past may have consisted of epochs of paroxysmal and catastrophic action, interposed between periods of comparative tranquility. Whewell argued for the principle of catastrophism, that occasionally huge catastrophes have altered the course of Earth history. Today, geologists know that Hutton's gradualism and Whewell's catastrophism are both correct. Over the great expanses of geologic time, slow, relatively uniform processes alter Earth. In addition, infrequent catastrophic events radically modify the path of slow change. Gradual change in Earth history. A good example of a slow but continuous Earth process is the movement of tectonic plates. Although too slow to be observed directly without sensitive instruments, over geologic time, the movement of tectonic plates alters the shapes of ocean basins, forms lofty mountains and plateaus, generates earthquakes and volcanic eruptions, and affects our planet in many other ways. Catastrophic change in Earth history. Although the chance that you will experience a large earthquake this year is very small, it nonetheless exists. In fact, deadly earthquakes occur each year somewhere on the planet. The largest recorded earthquake in the United States occurred in Alaska on September 2, 1964. Although the Alaskan earthquake caused significant loss of property and is attributed to 139 human deaths, 6 other catastrophic earthquakes have caused a greater loss of life and property in the 21st century: the 2011 Tohoku earthquake and tsunami in Japan, the 2004 Sumatra Andaman earthquake and tsunami in Indonesia, and large earthquakes that occurred in Haiti in 2010, Sichuan, China, in 2008, and Kashmir, Pakistan, in 2005. Though each horrific, even these catastrophes are minuscule compared with events that have occurred in the past. When geologists study the 4.6 billion years of Earth history, they find abundant evidence of catastrophic events that are highly improbable in a human lifetime or even in human history. For example, clues preserved in rock and sediment indicate that giant meteorites have smashed into our planet, vaporizing portions of the crust, spreading dense dust clouds over the sky, and leaving large craters. Geologists have suggested that some meteorite impacts have almost instantaneously driven millions of species into extinction. As another example, when the continental glaciers receded at the end of the last ice age, huge floods occurred that were massively larger than any floods during human history. In addition, periodically throughout Earth history, catastrophic volcanic eruptions have changed environmental conditions for life around the globe. Threshold and feedback effects. Earth systems often change in ways that are difficult to predict. 2 mechanisms that contribute to the challenges and complexities facing Earth science today are discussed next. Threshold effects. Consider a single rainstorm in Southern California. If the rain is gentle enough and it has not rained much recently, all of the rain falling will soak into the soil. If the rain lasts long enough or becomes heavy enough, a point will be reached where the soil becomes saturated and water begins to flow overland. Once runoff begins to flow across already saturated soil, a very different situation exists, especially on hill slopes where the overland flow runs together. There, even small additional increases in rainfall can cause the saturated soil to begin to move downslope as a landslide. Each year, landslides in Southern California are a serious threat, although widespread landsliding occurs only during especially wet years. The landslide shown in Figure 1.11 occurred in March 1995, following an unusually wet spring. Part of the landslide moved again in 2005, killing 10 people and causing millions of dollars in damage. A threshold effect occurs when the environment initially changes slowly in response to a small perturbation, or deviation from the norm in a system, but after the threshold is crossed, an additional small perturbation causes rapid and dramatic change. In the example above, the initial rainfall simply soaked into the soil, but once it became saturated and additional rain began to flow across the surface, the saturated soil could no longer maintain its slope and the landslide began to move. If we don't understand a system thoroughly, it is easy to be deluded into a false sense of complacency. Imagine, in the case just described, that we didn't know about landslide hazards. If we observed that normal amounts of rainfall simply soaked in or produced a muddy stream, we might conclude that a landslide was not possible. But once the threshold level of saturation was crossed, the landslide did begin to move. Populations of plants, animals, and people also respond to thresholds. In 1944, the U.S. Coast Guard released 29 reindeer onto St. Matthew Island in the Bering Sea as an emergency food supply for military personnel stationed there during World War II. The military withdrew from St. Matthew Island at the end of the war, and because there were no natural predators on the island, the reindeer population increased dramatically. In 1957, 13 years after the release of the reindeer, wildlife biologist Dave Klein visited the island and counted 1,350 reindeer, most of which appeared well-fed and healthy. To an untrained eye, the introduction was successful, because the reindeer were healthy and multiplying. But during that visit, Klein noticed some local overgrazing and trampling of lichens, foreshadowing trouble ahead. He returned in 1963 and counted 6,000 reindeer, although this time the average size was down, as was the ratio of adults to yearlings. Klein also noticed obvious signs of overgrazing during that trip. The reindeer herd was eating more food than was growing and was rapidly heading toward a threshold. Everything was fine as long as the reindeer could move across the island to find new sources of food, but when the entire island became overgrazed, suddenly there was nothing to eat, and the reindeer starved. When Klein next visited St. Matthew Island, in 1966, he was greeted by hundreds of bleached skeletons and counted only 41 emaciated survivors, a population drop of over 99% in 3 years or less. By the 1980s, all of the reindeer had perished. Feedback mechanisms. A feedback mechanism occurs when a small perturbation in one component affects a different component of Earth's systems, which then amplifies the original effect and perturbs the system even more, leading to an even greater effect. For example, as Earth warms, the rate at which organic matter in soil decomposes also increases. The increased rate of decomposition releases more carbon dioxide into the atmosphere. The additional carbon dioxide gas enhances the greenhouse effect, causing Earth's climate to warm further and promoting even faster rates of decomposition. Although no one fully understands the eventual ramifications of this feedback loop for Earth's climate, Chapter 21 explores what scientists do know. Humans and Earth systems 10,000 years ago, a mere eye blink in Earth history. Human population was low and technology was limited. Sparsely scattered bands hunted and gathered for their food, built simple dwellings, and warmed themselves with small fires. The impact of humans was not appreciably different from that of many other species on the planet. But with the invention of agriculture and the growth of cities, problems arose in some cultures. In his recent book Collapse, Jared Diamond documents several case histories where people settled in a region, built a society, and consumed resources faster than they were naturally replaced. Then, like the reindeer on St. Matthew Island, populations crashed. For example, at the height of the Mayan civilization, between the 3rd and the 9th centuries, between 5 and 15 million people are estimated to have lived in a region about 800 miles square, resulting in a population density of between 6,250 and 18,750 people per square mile. Then, due to a variety of human and environmental factors, the Mayan population crashed and the cities were abandoned, as an estimated 90 to 95% of the people died. In a similar manner, the Anasazi civilizations in the American Southwest disappeared in the 13th century, and Viking colonies starved to death in Greenland. All three of these human tragedies were exacerbated by climate change and human-to-human interactions, such as war. Nevertheless, Diamond points out that after thresholds were reached, the populations didn't just decline back to a sustainable level, rather, they collapsed catastrophically. As of June 2019, there were 7.7 billion people on Earth. Farms, pasturelands, and cities covered 40% of the land area of the planet. We diverted half of all the freshwater on the continents and controlled 50% of the total net terrestrial biological productivity. As the land and its waters have been domesticated and manipulated, other animal and plant species have perished. The species extinction rate today is 1,000 times more rapid than it was before the Industrial Revolution. In fact, species extinction hasn't been this rapid since a giant meteorite smashed into Earth's surface 65 million years ago, leading to the demise of the dinosaurs and many other species. We are presently living through the largest documented extinction on Earth since the age of the dinosaurs. Emissions from our fires, factories, electricity generating plants, and transportation machines have raised the atmospheric carbon dioxide concentration to its highest level in 420,000 years. Since the Industrial Revolution, Earth's mean annual temperature has increased by 0.8 degrees Celsius. Roughly 20% of the human population lives in wealthy industrialized nations where food, shelter, clean drinking water, efficient sewage disposal, and advanced medical attention are all readily available. As of 2016, 767 million people worldwide survived on less than $1.90 per day. 1/8 to 1/2 of the human population on this planet is malnourished, and 14 million infants or young children starve to death every year. If you were a member of a family in the Himalayan region of northern India, where you spent hours every day gathering scant firewood or cow dung for fuel, where meals consisted of an endless repetition of barley gruel and peas, where you brought your sheep and goats into the house during the winter so you could all huddle together for warmth, your experience of the Earth and its systems would be quite different from that of your life today. Yet no matter where we live and regardless of whether we are rich or poor, our survival is interconnected with the flow of energy and materials among Earth systems. We affect Earth, and at the same time Earth affects us. It is the most intimate and permanent of marriages. Predictions for the future are, by their very nature, uncertain. More than 200 years ago, in 1798, the Reverend Thomas Malthus argued that the human population was growing exponentially, while food production was increasing much more slowly. As a result, humankind was facing famine, accompanied by misery and vice. But technological advancements have led to an exponential increase in food production, and today food is plentiful in many regions. At the same time, however, serious shortages exist, especially in parts of Africa. Many scientists are deeply concerned about our future. John Holdren, professor at the John F. Kennedy School of Government, argues that, not that we are running out of energy, food, or water, but that we are running out of environment, that is, running out of the capacity of air, water, soil, and biota to absorb, without intolerable consequences for human well-being, the effects of energy extraction, transport, transformation, and use. 3 broad trends are currently facing humanity. 1. The human population is large and continuing to increase, although the rate of increase is slowing. As of June 2019, the U.S. Census Bureau estimated the world population at 7.6 billion. According to the United Nations, world population is projected to reach 9.8 billion in 2050, and 11.2 billion in 2100. 2. At the same time, extreme poverty is decreasing. In India and China, with 1/3 of the world's population, economic output and standards of living are rising rapidly. When people have money, they consume more resources. 3. As both population and per capita consumption rise, pollution and pressure on Earth's resources also continue to rise. Professor Diamond, quoted earlier, argues that we are in a horse race with the environment. One horse, representing increased human consumption and the resulting environmental degradation and resource depletion, is galloping toward an unsustainable society with a possible catastrophic collapse. The other horse, powered by improved technology, increased awareness, and declining rates of population growth, leads us toward a happy, healthy, sustainable society. Which horse will win? This book will not provide answers, because there are none, but it will provide a basis for understanding Earth processes so that you can evaluate and appreciate issues concerning our stewardship of the planet. The table highlighted in green below suggests an environmental to-do list. Key concepts review. Earth consists of 4 spheres. The geosphere is composed of a dense, hot, central core, surrounded by a large mantle that comprises most of Earth's volume, with a thin, rigid crust. The crust and mantle are composed of rock while the core is composed of iron and nickel. The hydrosphere is mostly ocean water. Most of Earth's fresh water is locked in glaciers. Most of the liquid freshwater lies in groundwater reservoirs. Streams, lakes, and rivers account for only 0.01% of the planet's water. The atmosphere is a mixture of gases, mostly nitrogen and oxygen. Earth's atmosphere supports life and regulates climate. The biosphere is the thin zone that life inhabits. A system is composed of interrelated, interacting components that form a complex whole. Earth's four major systems, the four spheres, are subdivided into a great many interacting smaller ones. All the spheres continuously exchange matter and energy. Earth is about 4.6 billion years old. Life formed at least 3.8 billion years ago. Abundant multicellular life evolved about 544 million years ago, and hominids have been on this planet for a mere 5 to 7 million years. The principle of gradualism states that geologic change occurs over a long period of time by a sequence of almost imperceptible events. In contrast, the principle of catastrophism postulates that geologic change occurs mainly during infrequent catastrophic events. A threshold effect occurs when the environment initially changes slowly in response to a small perturbation, but after the threshold is crossed, an additional small perturbation causes rapid and dramatic change. A feedback mechanism occurs when a small initial perturbation in one component affects a different component of Earth systems, amplifying the original effect, which perturbs the system even more and leads to an even greater effect. Due to our sheer numbers and technological prowess, humans have become a significant engine of change in Earth systems. Chapter 2, Minerals. Introduction. Minerals are the building blocks of rock, and therefore the geosphere is composed of minerals. Minerals make up soil and rock found at the Earth's surface, as well as the deeper rock of the crust and mantle. Any thorough study of Earth must include an understanding of minerals. But it is not sufficient to study minerals in isolation from the rest of the planet. Rather, we can learn more by observing the ways in which minerals interact with other Earth systems. Most minerals in their natural settings are harmless to humans and other species. In addition, many resources that are essential to modern life are produced from rocks and minerals: iron, aluminum, gold, and all other metals, concrete, fertilizers, coal, and nuclear fuels. Both oil and natural gas are recovered from natural reservoirs in rock. The discovery of methods to extract and use these earth materials has profoundly altered the course of human history. The Stone Age, the Bronze Age, and the Iron Age are historical periods named for the rock and mineral resources that dominated the development of civilization during those times. The Industrial Revolution occurred when humans discovered how to convert the energy stored in coal into useful work. The Automobile Age occurred because humans found vast oil reservoirs in shallow rocks of Earth's crust and built engines to burn the refined fuels. The Computer Age relies on the movement of electrons through wafer-thin slices of silicon, germanium, and other materials that are also crystallized from minerals. However, some minerals are naturally harmful. For example, uranium-bearing minerals are radioactive, while sulfide-bearing minerals can dissolve and release harmful elements including lead and arsenic into the environment. Some common minerals become harmful to humans when they are crushed to dust during mining, quarrying, road building, and other activities. In this chapter, we will consider the nature of minerals and then return to a discussion of minerals as natural resources and as environmental hazards. What is a mineral? Pick up any rock and look at it carefully. You may see small, differently colored specks, such as those you see in the close-up photo of granite in Figure 2. 1. Each speck is a mineral. In the photo, the white grains are the mineral feldspar, the black ones are biotite, and the glassy gray ones are quartz. A rock is a mixture of minerals. Most rocks contain 2 to 5 abundant minerals plus minor amounts of several others. Few rocks are made of only one mineral. Although we can define minerals as the building blocks of rocks, such a definition does not tell us much about the nature of minerals. More precisely, a mineral is a naturally occurring inorganic solid with a definite chemical composition and a crystalline structure. Chemical composition and crystalline structure are the two most important properties of a mineral. They distinguish any mineral from all others. Before discussing these two properties, however, let's briefly consider the other properties of minerals that this definition describes. Naturally occurring. A Synthetic diamond can be identical to a natural one, but it is not a true mineral, according to our definition, because a mineral must form by natural processes. Like diamonds, most other gems that occur naturally can be manufactured by industrial processes. Natural gems are more highly valued than manufactured ones. For this reason, jewelers should always tell their customers whether a gem is natural or artificial, by prefacing the name of a manufactured gem with the term synthetic. Inorganic organic substances are composed mostly of carbon that is chemically bonded to hydrogen. Inorganic compounds do not contain carbon-hydrogen bonds. Although organic compounds can be produced in laboratories and by industrial processes, plants and animals create most of Earth's organic material, because plant and animal tissue is organic. When these organisms die, they decompose to form other organic substances. Both coal and oil form by the decay of plants and animals. However, because of their organic properties and lack of a definite chemical composition, neither substance is a mineral. In addition, oil is a liquid, not a solid. Some material that organisms produce is not organic. For example, limestone, one of the most common sedimentary rocks, commonly contains debris from the shells or skeletons of invertebrate organisms such as clams, snails, and corals. The shells and skeletal pieces, in turn, typically are made of the minerals calcite and aragonite. Although the organisms produce the calcite and aragonite, both are a mineral, an inorganic solid that formed naturally and has a definite chemical composition and crystalline structure. Solid. All minerals are solids. Thus, ice is a mineral, but neither water nor water vapor is a mineral. The chemical composition of minerals. Minerals are the fundamental building blocks of rocks, but what are minerals made of? Minerals and all other earth materials are composed of chemical elements. An element is a fundamental component of matter that cannot be broken into simpler particles by ordinary chemical processes. Most common minerals consist of a small number of different chemical elements, usually 2 to 5. A total of 88 elements occur naturally in Earth's crust. However, 8 elements, oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium, make up more than 98% of the crust. Each element is represented by a 1 or 2 letter symbol, such as O for oxygen and C for silicon. In nature, most chemical elements have either a positive or negative electrical charge. For example, oxygen has a charge of -2 and silicon has a charge of +4. An atom with an electrical charge, whether it is positive or negative, is called an ion. A positively charged ion is a cation. An ion that has a negative charge is an anion. Ions with opposite charges are attracted to each other, like the positive end of a magnet attracts the negative end. Recall that a mineral has a definite chemical composition. A substance with a definite chemical composition is made up of elements that are combined in definite proportions. Therefore, the composition of a mineral can be expressed as a chemical formula, written by combining the symbols of the individual elements with the number of each within the repeating molecular unit that forms the mineral crystal. A few minerals, such as gold and silver, consist of only a single element. Their chemical formulas, respectively, are O and Ag. Most minerals, however, are made up of 2 to 5 essential elements. For example, the formula of quartz is Co. It consists of 1 atom of silicon for every 2 of oxygen. Quartz from anywhere in the universe has that exact composition. If it had a different composition, it would be some other mineral. The compositions of some minerals, such as quartz, do not vary by even a fraction of a percent. The compositions of other minerals vary slightly, but the variations are limited. The 88 elements that occur naturally in Earth's crust can combine in many ways to form many different minerals. In fact, more than 3,500 minerals are known. However, the 8 abundant elements commonly combine in only a few ways. As a result, only 9 rock-forming minerals make up most rocks of Earth's crust. We will describe the rock-forming minerals in section on mineral classes and the rock-forming minerals. The crystalline nature of minerals. Every mineral has a crystalline structure, and therefore every mineral is a crystal. A crystal is any solid element or compound whose atoms are arranged in a regular, periodically repeated three-dimensional pattern, like a wallpaper pattern that extends into 3 dimensions. The mineral halite has the composition NaCl, 1 sodium ion for every chlorine ion. Figure 2.2a is an exploded view of the ions in halite. Figure 2.2b is more realistic, showing the ions in contact. In both sketches, the sodium and chlorine ions alternate in orderly rows and columns intersecting at right angles. This orderly, repetitive arrangement of atoms is the crystalline structure of halite. Most minerals initially form as tiny crystals that grow as layer after layer of atoms are added to their surfaces. A halite crystal might grow, for example, as salty seawater evaporates from a tidal pool. At first, a tiny mineral grain might form, similar to the sketch of halite in Figure 2. This model shows a halite crystal containing 125 atoms. It would be only about 1/millionth of a millimeter long on each side, far too small to see with the unaided eye. As evaporation continues, more and more sodium and chlorine ions would precipitate onto the corners, edges, and faces of the growing crystal. A crystal face is a flat surface that develops if a crystal grows freely in an uncrowded environment, such as halite growing in a pool of evaporating seawater. When a mineral grows freely like this, it commonly forms a symmetrical crystal with perfectly flat faces that reflect light like a mirror. In nature, however, mineral crystals often impede the growth of adjacent crystals. For this reason, minerals rarely show perfect development of crystal faces. Figure 2.3 is a photomicrograph, a photo taken through a microscope of a thin slice of granite in which the crystals fit like pieces of a jigsaw puzzle. This interlocking texture developed because some crystals grew around others as molten magma cooled and solidified. Physical properties of minerals. If chemical composition and crystal structure distinguish each mineral from all others, how does a geologist identify individual minerals in the field? For example, halite always consists of sodium and chlorine in a 1-to-1 ratio, with the atoms arranged in a cubic fashion. But if you pick up a crystal of halite, you cannot see the atoms. You could identify a sample of halite by measuring its chemical composition and crystal structure using laboratory procedures, but such analyses are expensive and time-consuming. Instead, geologists commonly identify minerals by visual recognition and then confirm the identification with simple tests. Most minerals have distinctive appearances. Once you become familiar with common minerals, you will recognize them just as you recognize any familiar object. For example, an apple just looks like an apple, even though apples come in many colors and shapes. In the same way, quartz looks like quartz to a geologist. The color and shape of quartz may vary from sample to sample, but it still looks like quartz. Some minerals, however, look like others, so that their physical properties must be examined further to make a correct identification. For example, halite can look like calcite, quartz, and several other minerals, but halite tastes salty and scratches easily with a knife blade, two characteristics that distinguish it from the other minerals. Geologists commonly use properties such as crystal habit, cleavage, fracture, hardness, specific gravity, color, streak, and luster to identify minerals. Crystal habit refers to the characteristic shape of an individual crystal and the manner in which aggregates of crystals grow. If a crystal grows freely, it develops a characteristic shape that the arrangement of its atoms controls. Some minerals occur in more than one habit. For example, Figure 2.4a shows quartz with a prismatic habit, and Figure 2.4b shows a massive quartz in which numerous individual microscopic crystals intergrow to produce the habit. Cleavage is the tendency of some minerals to break along flat surfaces. The surfaces are planes of weak bonds in the crystal. Some minerals, such as the micas, have one set of parallel cleavage planes. Others have 2, 3, or even 4 different sets, as shown by the 3 photos in Figure 2. 6. In some cases, the expression of the cleavage is excellent. For example, you can peel sheet after sheet from a mica crystal as if you were peeling layers from an onion. In other cases, cleavage is not well developed. Many minerals, such as quartz, have no cleavage at all because they have no planes of weak bonds. The number of cleavage planes, the expression, or quality, of cleavage, and the angles between cleavage planes all help in mineral identification. A flat surface created by cleavage and a flat crystal face can appear to be very similar. However, a cleavage surface is repeated when a crystal is broken, whereas a crystal face is not. Fracture is the manner in which a mineral breaks other than along planes of cleavage. Many minerals fracture into characteristic shapes. For instance, a conchoidal fracture creates smooth, curved surfaces. It is characteristic of quartz and olivine. Some minerals break into splintery or fibrous fragments. Most fracture into irregular shapes. Hardness is the resistance of a mineral to scratching and is one of the most commonly used properties for identifying a mineral. It is easily measured and is a fundamental property of each mineral because it is controlled by the bond strength between the atoms in the mineral. Geologists commonly gauge hardness by attempting to scratch a mineral with the tip of a pocket knife. If the metal scratches the mineral is softer. If the knife tip cannot scratch the mineral is harder. To measure hardness more accurately, geologists use a scale based on 10 minerals, numbered 1 through 10. Each mineral is harder than those with lower numbers on the scale, so 10 is the hardest and 1 is the softest. The scale is known as the Mohs hardness scale, after Friedrich Mohs, the Austrian mineralogist who developed it in the early 19th century. As you can see from Table 2.2, the Mohs scale shows that a mineral scratched by quartz but not by orthoclase has a hardness between 6 and 7. Because the minerals of the Mohs scale are not always handy, it is useful to know the hardness values of common materials. A fingernail has a hardness of slightly more than 2, a pocket knife blade slightly more than 5, window glass about 5.5, and a steel file about 6. 5. If you practice with a knife and the minerals of the Mohs scale, you can develop a feel for minerals with hardness of 5 and under by seeing how easily the blade scratches them. When testing hardness, it is important to determine whether the mineral has actually been scratched by the object or the object has simply left a trail of its own powder on the surface of the mineral. 2. Check, rub away the powder trail and feel the surface of the mineral with your fingernail for the groove of the scratch. Fresh, unweathered mineral surfaces must be used in hardness measurements, because weathering often produces a soft rind. On minerals. Specific gravity is the weight of a substance relative to that of an equal volume of water. If a mineral weighs 2.5 times as much as an equal volume of water, its specific gravity is 2.5. You can estimate a mineral's specific gravity simply by hefting a sample in your hand. If you practice with known minerals, you can develop a feel for specific gravity. Most common minerals have a specific gravity of about 2.7. Metals have a much higher specific gravity. For example, the specific gravity of lead is 11.3, silver is 10.5, and copper is 8.9. Gold has the highest specific gravity of all minerals at 19. Color is the most obvious property of a mineral, and it is often used in identification. But color can be unreliable, because small amounts of chemical impurities and imperfections in crystal structure can dramatically alter color. For example, corundum is normally a cloudy, translucent, brown or blue mineral. The addition of a small amount of chromium can convert corundum to the beautiful, clear, red gem known as ruby. A small quantity of iron or titanium turns corundum into the striking blue gem called sapphire. Quartz also occurs in many colors, including white, clear, black, purple, and red, as a result of tiny amounts of impurities and minor defects in the perfect ordering of atoms. Streak refers to the color of the fine powder of a mineral. It is observed by rubbing the mineral across a piece of unglazed porcelain known as a streak plate. Many minerals leave a streak of powder on the plate with a diagnostic color. Streak is commonly more reliable for identification than the color of the mineral itself. For example, the mineral hematite can occur both as a dull red mineral and in a shiny black form that closely resembles black mica. But both types will leave the same red powder on a streak plate. Luster is the manner in which a mineral reflects light. A mineral with a metallic look, irrespective of color, has a metallic luster. Pyrite is a yellowish mineral with a metallic luster. As a result, it looks like gold and is commonly called fool's gold. The luster of nonmetallic minerals is usually described by self-explanatory words such as glassy, pearly, earthy, and resinous other properties. Properties such as reaction to acid, magnetism, radioactivity, fluorescence, and phosphorescence can be characteristic of specific minerals. Calcite and some other carbonate minerals dissolve rapidly in acid, releasing visible bubbles of carbon dioxide gas. The mineral magnetite displays an obvious, diagnostic attraction to magnets. Carnotite, a uranium-bearing mineral, emits radioactivity that can be detected with a scintillometer. Fluorescent materials emit visible light when they are exposed to ultraviolet light. Phosphorescent minerals continue to emit light after the external stimulus ceases. Mineral classes and the rock-forming minerals. Geologists classify minerals according to their anions or anionic groups. For example, silicates minerals all contain anionic groups made of silicon and oxygen bonded together to form -4. Carbonates minerals all contain the anionic group 2-, and sulfides contain the anion sulfide. The native elements are a small class of minerals, including pure gold and silver, that consist of only a single element. Although more than 3,500 minerals are known to be in Earth's crust, only a small number, between 50 and 100, are common or valuable, and only 9 rock-forming minerals make up most of the crust. These 9 are important to geologists simply because they are the most common and abundant minerals. 7 of the rock-forming minerals are silicate minerals. The other 2, calcite and dolomite, are carbonates. Silicate silicates make up about 92% of Earth's crust. They are abundant for 2 reasons. First, silicon and oxygen are the 2 most plentiful elements in the crust. Second, silicon and oxygen combine readily. To understand silicate minerals, remember that 1. Every silicon atom in a silicate mineral surrounds itself with 4 oxygen atoms. The bonds between silicon and its 4 oxygen atoms are very strong. 2. The silicon atom and its 4 oxygen atoms form a pyramid-shaped structure, called the silicate tetrahedron, with silicon in the center and oxygen at the 4 corners, as illustrated in the 2 panels of Figure 2. 9. The silicate tetrahedron is the fundamental building block of all silicate minerals. 3. Negatively charged silicate tetrahedra combine with positively charged elements in Earth's crust to form silicate minerals. The most common cations are aluminum, iron, calcium, potassium, sodium, and magnesium. Quartz is the only common silicate mineral that contains only silicon and oxygen. 4. Silicate tetrahedra commonly link together by sharing oxygen atoms to form chains, sheets, or 3-dimensional networks as shown in Figure 2.10. In all silicate minerals except quartz, the chains, sheets, and networks of silicate tetrahedra formed by the sharing of oxygens are negatively charged and must combine with positively charged cations to form a neutral silicate mineral. Rock-forming silicate. Tetrahedra in silicate minerals link together in 5 different ways, forming 5 different silicate mineral structures. Each structure contains at least one of the rock-forming minerals. Figure 2.10 displays these structures as well as the most common silicate minerals in each group. Figure 2.11 shows that feldspar alone makes up about half of Earth's crust. Feldspars are divided into 2 main groups: plagioclase feldspar that contains calcium and alkali feldspar that contains potassium or sodium instead of calcium. Orthoclase is a common alkali feldspar and is abundant in granite and other rocks of the continents. Rocks of the oceanic crust contain about 50% plagioclase. Plagioclase and orthoclase often look alike and can be difficult to tell apart in hand samples. Quartz comprises 12% of crustal rocks. It is widespread and abundant in most continental rocks but rare in oceanic crust and the mantle. Quartz is the only common silicate mineral that contains no cations other than silicon. It is pure CO. It has a ratio of 1:4 silicon for every 2 oxygens, so the positive and negative charges neutralize each other perfectly without the addition of other cations. Pyroxene makes up another 11% of the crust. The basalt rock of ocean crust is made up almost entirely of two minerals, plagioclase feldspar and pyroxene. Basalt commonly contains 1 or 2% olivine, but olivine is otherwise uncommon in Earth's crust. However, it makes up a large proportion of mantle rocks, and thus is an abundant and important mineral. Amphibole, mica, and clay are the other rock-forming silicate minerals. Amphiboles and micas are common in granite and many other types of continental rocks but are rare in oceanic crust. Clay forms when rain and atmospheric gases chemically decompose other silicate minerals, and thus clay is common in soils. Clay minerals are especially common in mudstone, which is the most abundant of all carbonates. Carbonate minerals are much less common overall than silicates in Earth's crust, but many sedimentary rocks are formed from carbonate minerals, and these now cover large regions of every continent, as described in the following chapter. The shells and other hard parts of many marine organisms, including clams, snails, corals, and even certain types of plankton and green algae, are made of carbonate minerals. The hard pieces accumulate to form the abundant sedimentary rock called limestone, which is comprised of calcite and is a rock type mined as a raw ingredient of cement. Another very common carbonate mineral is dolomite, which forms a rock also called dolomite or dolostone. Commercially important minerals. Many minerals are commercially important even though they are not abundant. Our industrial society depends on metals such as iron, copper, lead, zinc, gold, and silver. Ore minerals are minerals from which metals or other elements can be profitably recovered. A few, such as native gold and native silver, are composed of a single element. However, most metals are chemically bonded to other elements. Iron is commonly bonded to oxygen. Copper, lead, and zinc are commonly bonded to sulfur to form sulfide or minerals, such as the galena in Figure 2.13. Industrial minerals are not metal ores, fuels, or gems but have economic value nonetheless. Halite is mined for table salt, and gypsum is mined for plaster and sheetrock. Apatite and other phosphatic minerals are sources of the phosphate fertilizers crucial to modern agriculture. Calcite is a raw ingredient of cement. Native sulfur, used to manufacture sulfuric acid, insecticides, fertilizer, and rubber, is mined from the craters of dormant and active volcanoes, where it is deposited from gases emanating from the vents, like the one in Figure 2.14. A gem is a mineral that is prized primarily for its rarity and/or beauty, although some gems, such as diamonds, are also used industrially. Depending on its value, a gem can be either precious or semi-precious. Precious gems include diamond, emerald, ruby, and sapphire. Several varieties of quartz, including amethyst, agate, jasper, and tiger's eye, are semi-precious gems. Garnet, olivine, topaz, turquoise, and many other minerals can also occur as attractive semi-precious gems. When you look at a lofty mountain or a steep cliff, you might not immediately think about the tiny mineral grains that form the rocks. Yet minerals are the building blocks of Earth. In addition, some minerals provide the basic resources for our industrial civilization. As we will see throughout this book, Earth's surface and the human environment change as minerals react with the air and water, with other minerals, and with living organisms. Harmful and dangerous rocks and minerals. Most rocks and minerals in their natural states are harmless to humans and other organisms. That is not surprising, because all of us evolved among the minerals and rocks that make up Earth, and species would not survive if they were poisoned by their surroundings. A few rocks and minerals, however, are harmful and dangerous. Asbestos is one such mineral. It is a powerful carcinogen, a cancer-causing substance. Some rocks and minerals emit radon gas, a radioactive carcinogen. Other rocks and minerals contain toxic elements such as mercury, lead, arsenic, uranium, and sulfur. In nature, most environmentally hazardous rocks and minerals are buried beneath the surface, where they are unavailable to plants and animals. Natural weathering and erosion expose them so slowly that they do little harm. Most minerals that contain toxic metals or other elements such as lead, mercury, and arsenic are also relatively insoluble. In most natural environments, they weather so slowly that they release the toxic materials in low concentrations. However, if pollution controls are inadequate, mining, milling, and smelting can concentrate and release hazardous natural materials at greatly accelerated rates, poisoning humans and other organisms. Silicosis and black lung. Most common minerals such as feldspar and quartz are harmless in their natural states in solid rock. However, if these minerals are ground to dust, they can enter the lungs and cause serious and even fatal inflammation and scarring of the lung tissue, called silicosis. In advanced cases, the lungs become inflamed and may fill with fluid, causing severe breathing difficulty and low blood oxygen levels. On-the-job exposure to silica dust can occur in mining, stonecutting, quarrying, building and road construction, working with abrasives, sandblasting, and other occupations and hobbies. Intense exposure to silica may produce silicosis in a year or less, but it usually takes at least 10 or 15 years of exposure before symptoms develop. Silicosis has become less common since the Occupational Safety and Health Administration instituted regulations requiring the use of protective equipment that limits the amount of silica dust inhaled. Coal dust, inhaled by coal miners in large quantities before federal laws required dust suppression in coal mines, has similar effects and causes a disease called black lung. Asbestos, asbestosis, and cancer. Asbestos is an industrial name for a group of minerals that crystallize as long, thin fibers. One type is a sheet silicate mineral called chrysotile, which has a crystal structure and composition similar to that of the micas and which forms tangled, curly fibers. The other type of asbestos includes 4 similar varieties of amphibole that crystallize as straight, sharply pointed needles. Chrysotile has been the more valuable and commonly used type of asbestos, because the fibers are flexible and tough and can be woven into fabric. It was considered to be a less harmful form because some believed its curly fibers would be more easily expelled from the lungs. However, recent studies show that all forms of asbestos are carcinogenic. Asbestos is commercially valuable because it is flameproof, chemically inert, and extremely strong. For example, chrysotile fibers are 8 times stronger than a steel wire of equivalent diameter. Asbestos has been used to manufacture brake linings, fireproof clothing, insulation, shingles, tile, pipe, and gaskets, but now is allowed only in brake pads, shingles, and pipe. In the early 1900s, asbestos miners and others who worked with asbestos learned that prolonged exposure to the fibers caused an irreversible respiratory disease called asbestosis. Later, in the 1950s and 1960s, studies showed that asbestos also causes lung cancer and other forms of cancer. One reason that so much time passed before scientists recognized the cancer-causing properties of asbestos is that the disease commonly does not develop until decades after exposure. Although it is not clear how asbestos fibers cause cancer, it seems that the shapes of the crystals play an important role. Statistical studies also show that the sharp, pointed amphibole asbestos is a more potent carcinogen than the flexible chrysotile fibers, although both types cause cancer. In response to growing awareness of the health effects of asbestos, the Environmental Protection Agency banned its use in building construction in 1978. However, the ban did not address the issue of what should be done with the asbestos already installed. In 1986, Congress passed a ruling called the Asbestos Hazard Emergency Response Act, requiring that all schools be inspected for asbestos. Public response has resulted in hasty programs to remove asbestos from schools and other buildings, at a cost of billions of dollars. But what is the real level of hazard? Most asbestos in buildings is the less potent chrysotile, woven into cloth or glued into a tight matrix, and often the surface has been further stabilized by painting. Therefore, the fibers are not free to blow around. The levels of airborne asbestos in most buildings are no higher than those in outdoor air. Some scientists argue that asbestos insulation, despite being carcinogenic, poses no health danger if left alone, but when the material is removed, it is disturbed and asbestos dust escapes. Not only are workers endangered, but airborne asbestos can persist in a building for months after completion of an asbestos removal project. Radon and Cancer. Radon is one of a series of elements formed by the radioactive decay of uranium. Uranium occurs naturally in small concentrations in several minerals and in all types of rock, but it concentrates in two abundant rocks, granite and mudstone, that are described in the next chapter. It is also found in soil that formed from granite and mudstone, and in construction materials made from those rocks, such as aggregate or concrete. Radon is itself radioactive, and it decays quickly into other radioactive elements. Because of their radioactivity, radon and its decay products are carcinogenic, and because it is a gas, we inhale radon into our lungs. Radon seeps from the ground into homes and other buildings, where it concentrates in indoor air and causes an estimated 5,000 to 20,000 cancer deaths per year among Americans. The risk of dying from radon-caused lung cancer in the United States is about 0.4% over a lifetime, much greater than the risk of dying from cancer caused by asbestos, pesticides, or other air pollutants, and nearly as high as the risk of dying in an auto accident, from a fall, or in a fire at home. Not all Americans are exposed to equal amounts of radon. Some homes contain very low concentrations of the gas, others have high concentrations. The variations in concentration are due to two factors: geology and home ventilation. Geology is important because some types of rocks, such as granite and mudstone, contain high concentrations of uranium and radon, while others contain relatively little. As radon forms through the slow radioactive decay of uranium in bedrock, soil, or construction materials, it seeps into the basement of a home and circulates throughout the house. Radon concentrations are highest in poorly ventilated homes built on granite or mudstone, built on soil derived from these rocks, or constructed with concrete and concrete blocks containing these types of rocks. The highest home radon concentrations ever measured were found in houses built on the Reading Prong, a uranium-rich body of granite extending from Reading, Pennsylvania, through northern New Jersey and into New York. The air in one home in this area contains 700 times more radon than the EPA action level, the concentration at which the EPA recommends that corrective measures be taken to reduce the amount of radon in indoor air. People should ask two questions in regard to radon hazards. What is the radon concentration in my home, and, if it is high, what can be done about it? Because radon is radioactive, it can be measured with a simple detector available at most hardware stores or from local government agencies, for about $25. If the detector indicates excessive radon, several solutions are possible for lowering the radon level. One solution is to extend a ventilation duct either from the basement or from below the basement floor to the outside of the house. The ventilation duct prevents radon from accumulating in or below the basement by venting it directly to the outdoors. Another solution is to pump outside air into the house to keep indoor air at a slightly higher pressure than the outside air. This positive pressure prevents gas from seeping from soil or bedrock into the basement. Despite these solutions for lowering radon levels, it is impossible to avoid exposure to radon completely, because it is everywhere, in outdoor air as well as in homes and other buildings. But it is relatively easy and inexpensive to minimize exposure and thus avoid a significant cause of cancer. Acid mine drainage and heavy metals contamination. Sulfide or minerals are combinations of metals such as lead, zinc, copper, cadmium, mercury, and other heavy metals addition to the metals. These minerals are mined for their metals, which are essential to modern industrial societies. However, mining and refining sulfide or minerals can create serious air and water pollution problems. When these minerals are mined or refined without adequate pollution control, sulfur escapes into streams, groundwater, and the atmosphere, where it forms hydrogen sulfide and sulfuric acid. Waterborne sulfides poison aquatic organisms, and atmospheric sulfur compounds contribute to acid precipitation. The sulfuric acid that forms from the weathering of sulfide or minerals can cause other minerals from the rock in and around the mining site to be dissolved. Dissolution of these minerals releases into solution the metals they contain in their crystal structure. Once dissolved, the metals can quickly become part of the groundwater and surface water systems if not contained. Arsenic, lead, zinc, and copper are several of the metals that are common pollutants in areas affected by acid mine drainage. Chapter 3, Rocks. Introduction. Earth is solid rock to a depth of 2,900 kilometers, where the mantle meets the liquid outer core. Even casual observation reveals that rocks are not all alike. The Great Peaks of the Sierra Nevada in California are hard, strong granite. The red cliffs of the Utah desert are soft sandstone. The top of Mount Everest is limestone, containing the fossil remains of small marine invertebrates. The marine fossils atop Mount Everest tell us that this limestone formed in the sea. What forces lifted the rock to the highest surface elevation on Earth? Where did the vast amounts of sand in the Utah sandstone come from? How did the granite of the Sierra Nevada form? All of these questions ask about the processes that formed the rocks and changed them throughout geologic history. In this chapter, we will study rocks, what they are made of, and how they form. Rocks and the rock. CYCL. Rock is solid aggregate of one or more minerals. Based on how the rocks form, geologists define three main categories: igneous rocks, sedimentary rocks, and metamorphic rocks. Earth's interior is hot and dynamic. The high temperature that exists within a few hundred kilometers of the surface can cause solid rock to melt, forming a molten liquid called magma. Because the liquid magma is less dense than the surrounding solid rock, the magma rises slowly toward Earth's surface. As it rises, the magma cools. Igneous rock forms when cooling magma solidifies. All rocks may seem permanent and unchanging over a human lifetime, but this apparent permanence is an illusion created by our short observational time frame. Over geologic time, water and air attack rocks of all kinds at Earth's surface through the process called weathering, breaking them down into smaller particles. These particles, including gravel, sand, clay, and all other fragments weathered and eroded from rock, are transported away from the site of weathering by streams, glaciers, wind, and gravity. The particles eventually accumulate in loose, unconsolidated layers called sediment. Sand on a beach and mud on a lake bottom are examples of sediment. Sedimentary rock forms when sediment particles become cemented or compacted into solid rock. Weathering processes also form dissolved ions such as sodium, calcium, and chloride. Weathering of solid rock causes some of the minerals in it to change or dissolve altogether, thereby liberating positively charged cations and negatively charged anions. These ions are transported away from the site of weathering by streams and groundwater. Many households contain water softeners to remove these dissolved ions so that they don't precipitate and clog the home's plumbing system. Most of the dissolved ions formed by weathering eventually are carried to the sea. There, marine organisms such as clams, oysters, and corals extract dissolved calcium from seawater. They combine the calcium with carbon dioxide that dissolves in seawater from Earth's atmosphere, and use it to form their shells and other hard parts. After the organisms die, the remains of those shells accumulate. Precipitation of mineral cements between the shells and other particles results in the formation of sedimentary rock called limestone. Thus, limestone, one of the most common sedimentary rocks, forms by direct interactions among the geosphere, the hydrosphere, the biosphere, and the atmosphere. A metamorphic rock forms when heat, pressure, or hot water alters any pre-existing rock. For example, when rising magma intrudes the Earth's crust, it heats the rock around it. Although the heat may not be sufficient to melt rock surrounding the magma, it can bring about other changes. For example, the mineral crystals in the heated rock may grow or change their internal arrangement. Such alterations in the size, shape, and arrangement of mineral crystals within the rock are changes in the rock's texture. In addition, temperature and pressure within the Earth's crust may cause entirely different mineral types to grow that are stable at those changed temperatures and pressures. Thus, the process of metamorphism can change both the texture and mineral types within a pre-existing rock. Unlike igneous rocks, however, metamorphic rocks form without completely melting. No rock is permanent over geologic time. Instead, all rocks undergo processes that change them from one of the three rock types to another. This continuous process is called the rock cycle. For example, as sediment accumulates and is buried, it typically cements together to form a sedimentary rock. If sedimentary rock at the bottom of the accumulation is buried deeply enough, the rising temperature and pressure will cause it to convert to a metamorphic rock as it undergoes changes in texture and mineral composition. With additional burial and temperature increase, the metamorphic rock can melt, forming magma. The magma will then rise in the crust, slowly cool, and solidify to become igneous rock. Millions of years later, movement of Earth's crust might raise the igneous rock to the surface, where it will weather to form sediment. Rain and streams will then wash the sediment into a new basin, renewing the cycle. The rock cycle does not follow a set order and can take many different paths. For example, all three rock types can melt to form magma and, eventually, an igneous rock. Similarly, all three rock types can be weathered to form sediment or can be metamorphosed through changes in texture and mineral composition. The term rock cycle simply expresses the idea that rocks are not permanent but change over geologic time. The rock cycle and Earth systems interactions. The rock cycle illustrates several types of Earth systems interactions among rocks, the atmosphere, the biosphere, and the hydrosphere. Rain and air, aided by acids and other chemicals secreted by plants, decompose solid rocks to form large amounts of clay and other sediment. During these processes, water and atmospheric gases react chemically and become incorporated into the clay. Thus, these processes transfer water and air from the atmosphere and hydrosphere to the solid minerals of the geosphere. More rain then washes the clay and other sediment into streams, which carry it to a sedimentary basin where the clay is deposited. The rock cycle is also driven by Earth's internal heat. For example, when layers of sediment are deposited and buried by younger layers, the deeper layers become heated and metamorphosed by Earth's heat. The same heat may melt the rocks to produce magma. But then the magma rises upward and perhaps even erupts onto Earth's surface from a volcano. In this way, heat is transferred from Earth's interior to the atmosphere. Throughout this chapter, we emphasize these and other interactions among the atmosphere, biosphere, hydrosphere, and rocks of the geosphere to illustrate the point that those systems continuously exchange both energy and material so that Earth functions as a single integrated system. Igneous rocks. Magma, the source of igneous rocks. If you drill a well deep into in the middle of one of Earth's continents, you would find that the temperature within the crust rises about 30 degrees Celsius for every kilometer of depth. In the mantle between depths of 100 and 350 kilometers, the temperature is so high that rocks in some areas melt to form magma. Depending on its chemical composition and the depth at which it forms, the temperature of magma varies from about 600 degrees Celsius to 1,400 degrees Celsius. As a comparison, an iron bar turns red hot at about 600 degrees Celsius and melts at slightly over 1,500 degrees Celsius. Unlike ice, which decreases in volume when it melts to form water, rocks increase in volume when they melt. When a rock melts to form magma, it expands by about 10%, so it is less dense than the rock around it and therefore rises as it forms, much as a hot air balloon ascends in the atmosphere. When magma rises, it enters the cooler environment near Earth's surface, where it solidifies to form solid igneous rock. In addition, unlike ice that melts completely above 0 degrees Celsius, rocks do not melt completely at a single temperature because each mineral in the rock has its own unique melting temperature. For example, quartz melts at about 500 degrees Celsius, depending on the pressure, whereas the mineral olivine can reach temperatures in excess of 1,100 degrees Celsius. The result is that magma forming from melting rocks commonly has a different composition than the original rock because typically only those minerals with the lowest melting temperature melt, leaving behind those minerals with higher melting temperatures. The fact that different minerals melt, and freeze or crystallize, at different temperatures results in much of the variety of igneous rock types found on Earth. Types of igneous rocks. Some igneous rocks form when magma solidifies within Earth's crust. Other igneous rocks are created when magma erupts onto the surface. When magma solidifies, it usually crystallizes to form minerals. As magma cools, different minerals crystallize at different points during the cooling history. The minerals do not all crystallize at once. The size, shape, and arrangement of mineral crystals in an igneous rock are referred to as the rock's texture. Although some igneous rocks consist of mineral crystals that are too small to be seen with the unaided eye, others are made up of thumb-sized, or even larger, crystals. Extrusive rocks. When magma rises all the way through the crust to erupt onto Earth's surface, it forms extrusive igneous rock, also called volcanic rock. Lava is fluid magma that flows from a crack or a volcano onto Earth's surface. The term also refers to the rock that forms when lava cools and becomes solid. After lava erupts onto the relatively cool Earth's surface, it solidifies rapidly, in a period ranging from a few days to a few years. Crystals form but do not have much time to grow. As a result, many volcanic rocks consist of crystals too small to be seen with the unaided eye. Basalt is a common, very finely crystalline volcanic rock. If erupting lava encounters glacial ice or cold seawater, it may solidify or quench within a few hours of erupting. Because the magma hardens so quickly, the atoms have no time to align themselves to form crystals. As a result, the atoms are frozen into a random chaotic pattern, as happens in glass. Volcanic glass is called obsidian. If magma rises slowly through the crust before erupting, some crystals may grow, while most of the magma remains molten. If this mixture of magma and crystals then erupts onto the surface, the magma solidifies quickly, forming porphyry, a rock with large crystals, called phenocrysts, embedded in a finely crystalline matrix called ground mass. Intrusive rocks. When magma solidifies within the crust, without erupting to the surface, it is an intrusive igneous rock, also called Plutonic rock, named after the Greek god of the underworld. The rock overlying the magma insulates it like a thick blanket, providing hundreds of thousands, or even millions, of years for the magma to crystallize. As a result, most plutonic rocks are medium to coarsely crystalline. Granite, the most abundant rock in continental crust, is a medium or coarsely crystalline plutonic rock. The crystals in granite are clearly visible. Many are a millimeter or so across, although some crystals may be much larger. Naming and identifying igneous rocks. Geologists have different names for igneous rocks based on their minerals and texture. Let's take for example two rocks consisting mostly of feldspar and quartz. Medium or coarsely crystalline igneous rock made up of these minerals is called granite. When igneous rock with these minerals is very finely crystalline, it is called rhyolite. You can see the difference in the panels of figure 3.3. The same magma that solidifies slowly within the crust to form granite can also erupt onto Earth's surface to form rhyolite. Like granite and rhyolite, most common igneous rocks are classified in pairs, with the two members of a pair containing the same minerals but with different crystal sizes. The crystal size depends mainly on whether the rock is volcanic or plutonic. The specific suite of minerals that make up an igneous rock determines the rock's composition. Igneous rock compositions fall along a spectrum from those containing the most silica, like granite and rhyolite that have so much silica that the mineral quartz is common, to those with so little silica that Quartz is entirely absent, and most of the minerals that do form are instead rich in iron and magnesium. Silica-rich igneous rocks are called felsic, whereas those with little silica and abundant iron and magnesium are called mafic. Ultramafic rocks contain exceptionally low levels of silica and high concentrations of iron and magnesium-bearing minerals. Igneous rocks with intermediate levels of silica simply are called intermediate in composition. Understanding differences in the composition of igneous rocks is important because these differences relate directly to the geologic setting in which a magma forms, providing important clues to earlier parts of Earth's history. In addition, magma composition plays a direct control on how powerful a volcanic eruption can be. The largest, most catastrophic volcanic eruptions involve felsic magmas because the abundance of silica in the magma increases its viscosity, or stiffness, requiring the volcano to build up more internal pressure before erupting. Once you learn to identify the rock-forming minerals in an igneous rock, it is easy to name a coarsely crystalline plutonic rock because the minerals are large enough to see. It is more difficult to name many volcanic rocks, because the minerals commonly are too small to identify. A field geologist often uses color to name a volcanic rock. Rhyolite is usually light in color because the silica-rich minerals characteristic of felsic rocks, such as quartz and feldspar, are light-colored. Basalt is commonly black because of the abundance of dark-colored iron and magnesium-bearing minerals. Many andesite rocks are gray or green. In addition to using color to help identify different volcanic rocks, geologists use the heft of a rock to judge how dense it is. Ultramafic and mafic igneous rocks rich in iron and magnesium-bearing minerals are notably more dense than felsic rocks in which these minerals are relatively uncommon, common igneous rocks. Before proceeding with our discussion, you should become familiar with some terminology. Geologists commonly use the terms basement rock, bedrock, parent rock, and country rock. Bedrock is the solid rock that lies beneath soil or unconsolidated sediments. It can be igneous, metamorphic, or sedimentary. Parent rock is any original rock before it is changed by weathering, metamorphism, or other geological processes. The rock that already exists in an area and that is crosscut by younger intrusive igneous rocks or minerals deposits is called country rock. Basement rock is the igneous and metamorphic rock that lies beneath the thin layer of sediment and sedimentary rocks covering much of Earth's surface, thus forming the basement of the crust. Granite and rhyolite as discussed above. Granite contains mostly feldspar and quartz. Small amounts of black biotite or hornblende often give it a speckled appearance. Granite is the most common rock in continental crust. It is found nearly everywhere as basement rock, beneath the relatively thin veneer of sedimentary rocks and soil that covers most of the continents. Granite is hard and resistant to weathering. It forms steep, sheer cliffs in many of the world's great mountain ranges. Mountaineers prize granite cliffs for the steepness and strength of the rock. As granitic magma rises through Earth's crust, some of it may erupt from a volcano to form rhyolite, while the remainder solidifies beneath the volcano, forming granite. Most obsidian forms from magma with a granitic composition. Today, an active granitic magma body that has erupted large volumes of rhyolite and produced abundant rhyolitic obsidian in the recent geologic past is the Yellowstone volcano, where magma is located only a few kilometers below the surface. Over the past 1 million years, the Yellowstone volcano has produced 3 catastrophic eruptions that have covered much of the continent with volcanic ash. In addition to these highly explosive eruptions, numerous flows of rhyolite have spread across the volcano, largely filling in its central crater. The longest of the flows are tens of kilometers in length, and several of the flows have an outer sheath of obsidian that formed by rapid quenching of the rhyolite by water or glacial ice. Basalt and gabbro basalt consists of approximately equal amounts of plagioclase feldspar and pyroxene. It makes up most of the oceanic crust, as well as huge basalt plateaus on continents. Gabbro is the plutonic equivalent of basalt. It is mineralogically identical but consists of larger crystals. Gabbro is uncommon at Earth's surface, although it is abundant in deeper parts of the oceanic crust, where basaltic magma crystallizes slowly. In North America, basalt is particularly abundant across much of the Pacific Northwest, where a gigantic volume of basaltic magma erupted numerous times to form the Columbia River Plateau basalts about 17 million years ago. In addition, basalt is common across much of the Great Basin of Utah and Nevada, where it is forming due to tectonic stretching of the crust and partial melting of the upper mantle. A particularly famous basalt locality is the Hudson River Valley in New York, where the Palisades basalt formed about 175 million years ago as North America and Africa broke apart. Andesite and diorite. Andesite is a volcanic rock intermediate in composition between basalt and granite. It is commonly gray or green and consists of plagioclase, feldspar, and dark minerals. It is named for the Andes Mountains, the volcanic chain on the western edge of South America, where andesite is abundant. Because it is volcanic, andesite is typically very fine-grained. Diorite is the plutonic equivalent of andesite. It forms from the same magma as andesite and, consequently, often underlies andesitic mountain chains such as the Andes. Andesite is most common in volcanic chains, like the Andes, that are called volcanic arcs because they typically form an arc-like pattern on geologic maps. Volcanic arcs are developed at plate boundaries where one tectonic plate descends beneath another and is slowly melted in the process. The Cascade Mountains of the Pacific Northwest are such a volcanic arc and are made mostly of andesite and diorite. The Aleutian Island chain of Alaska is another volcanic arc where diorite and andesite are forming. Today, peridotite and komatiite. Peridotite is an ultramafic, rich in magnesium and iron, igneous rock that makes up most of the upper mantle but is rare in Earth's crust. It is coarse-grained and composed of olivine and small amounts of pyroxene, amphibole, or mica, but not feldspar. Komatiite is the finely crystalline, extrusive equivalent of peridotite. It is a rare rock type at the surface of today's Earth because modern volcanoes do not erupt ultramafic magma. It's simply too dense to reach the surface and must pass through a much more felsic crust with minerals that melt at low temperatures before reaching the surface. However, during the early parts of Earth's history more than 4 billion years ago, the first crust to form from the molten planet was made of ultramafic rock. As a result, komatiites formed abundantly during Earth's early history, but today, they are preserved only in those few localities in which rocks of this age are preserved. Sedimentary rocks over geologic time. The atmosphere, biosphere, and hydrosphere weather rock, breaking it down to gravel, sand, silt, clay, and ions dissolved in water. Weathering of rocks occurs by both chemical and physical processes. Glaciers, flowing water, gravity, and wind all erode the rock, transport the rock fragments downslope, and deposit them at lower elevations. Dissolved ions resulting from weathering also are transported downslope, commonly all the way to the sea, where the ions are concentrated. Marine organisms such as clams, snails, certain kinds of green algae, and corals use some of these ions to form shells and other hard parts. After the organisms die, these hard parts accumulate to form limestone. Other ions can react chemically to produce a solid salt, through the process of precipitation. For example, the mineral halite precipitates from a lake on the floor of Death Valley. Sedimentary rocks make up only about 5% of Earth's crust. However, because they form on Earth's surface, sedimentary rocks are widely spread in a thin veneer over underlying igneous and metamorphic rocks. As a result, they cover about 75% of continents. Sedimentary rocks are broadly divided into 4 categories. 1. Clastic sedimentary rock is composed of particles of weathered rocks, such as sand grains and pebbles, called clasts, which have been transported, deposited, and lithified. This category includes conglomerate, sandstone, and mudstone. Clastic sedimentary rock makes up about 85% of all sedimentary rock. 2. Organic sedimentary rock consists of the lithified remains of plants or animals. Coal is an organic sedimentary rock that contains such a high percentage of decomposed and compacted plant remains that the rock itself will burn. 3. Chemical sedimentary rock forms by direct precipitation of minerals from solution. Rock salt, for example, forms when halite precipitates from evaporating seawater or saline lake water. 4. Bioclastic sedimentary rock is composed of broken shell fragments and similar remains of living organisms. The fragments are clastic, but they have a biological origin. Many limestones are formed from broken shells and thus are bioclastic sedimentary rocks. Clastic sedimentary rocks. Clastic sediment is called gravel, sand, silt, or clay, in order of decreasing particle size. Table 3.2 shows the main sediment particle sizes and their corresponding diameters. As clastic particles ranging in size from boulders to coarse silt tumble downstream, their sharp edges are worn off and they become rounded. Finer silt and clay do not round effectively because they are so small and light that water and wind cushion them as they are buffeted along. If you hold a pile of sand in your hand and dribble water onto it, the water will soak into the empty zone, called pore space, among the sand grains. Commonly, sand and similar sediment have about 20 to 40% pore space. As we will see in Chapter 5, this pore space is very important because it is where economic quantities of water, petroleum, and natural gas typically occur. As sediment accumulates and is buried, it is compressed by the weight of the overlying layers. The compression partially collapses the pore spaces between sediment grains, forcing water out. This process is called compaction. As sediment is buried and compacted, groundwater slowly circulates through the remaining pore space. This water commonly contains dissolved ions that can precipitate in the pores, forming cement that binds the clastic grains firmly together into a hard rock. Calcite, quartz, and iron oxides are the most common cements in sedimentary rocks. The time required for lithification of sediment varies greatly. In some heavily irrigated areas of Southern California, calcite has precipitated from irrigation water to cement soils within only a few decades. In the northern Rocky Mountains, calcite has cemented some glacial deposits that are less than 20,000 years old. In contrast, sand and gravel deposited on the coastal plain of New Jersey as long ago as 95 million years can still be dug with a hand shovel. Conglomerate is lithified gravel. Each clast in a conglomerate is usually much larger than the individual mineral grains in the clast. In many conglomerates, the clasts may be fist-sized or even larger and therefore retain most of the characteristics of the parent rock. If enough is known about the geology of an area where conglomerate is found, it may be possible to identify exactly where the clasts originated. For example, a granite clast probably came from nearby granite bedrock. The next time you walk along a gravelly stream bed, look carefully at the gravel. You will probably see sand or silt trapped among the larger clasts. In a similar way, most conglomerates contain fine sediment among the large clasts. Sandstone consists of lithified sand grains. The sand forms from the physical and chemical breakdown of pre-existing rock. For example, weathering of granite typically produces sand-sized grains of quartz, feldspar, and other minerals. Streams, wind, glaciers, and gravity all can carry downslope sand formed by weathering. Sand grains carried in streams and by wind repeatedly undergo collisions as they bounce along. These impacts wear the sharp edges off of each grain, causing it to become rounded. Eventually, the sand grains accumulate to form a deposit of sand. Following burial, the deposit compacts and lithifies to form sandstone. Many sandstones consist predominantly of rounded quartz grains, because this hard mineral resists physical and chemical breakdown and therefore is concentrated by long periods of weathering and transport. Mudstone is a clastic sedimentary rock that consists mostly of tiny clay minerals and lesser amounts of silt and organic particles. Mudstone can vary widely in color, ranging from red to green to black. When weathered, some mudstone splits easily along very fine layering, called fissility. Such fissile mudstone usually is dark colored due to the presence of abundant organic matter. As it is buried, this organic matter can convert to oil and gas, which is slowly expelled from the mudstone and rises toward the surface through pore spaces in the rock. In Chapter 5, we will learn how recent technological developments that permit the direct drilling and hydraulic fracturing of organic-rich black mudrock has resulted in entirely new sources of oil and organic sedimentary rocks. Organic sedimentary rocks form by lithification of the remains of plants and animals. Coal is perhaps the most obvious example of an organic sedimentary rock, containing so much organic matter that the rock will burn. Coal forms from the accumulation of peat in swamps and similar environments where dead plants accumulate faster than they can be broken down by decay. As peat is buried and compacted by overlying sediments, it is lithified and converts to coal. Figure 3.19. Chemical sedimentary rock. Some common elements in rocks and minerals, such as calcium, sodium, potassium, and magnesium, dissolve during chemical weathering and are carried by groundwater in streams downslope. Most streams eventually reach the sea, but some streams are landlocked and end instead in a lake with no outlet, such as the Great Salt Lake in Utah. No streams exit such lakes, rather, water escapes only by evaporation or downward seepage. When the water evaporates, salts remain behind and the lake water becomes steadily saltier. Evaporites are rocks that form when evaporation concentrates the salts to the point at which they precipitate from solution. The same process can occur if ocean water is trapped in coastal or inland basins where it can no longer mix with the open sea. A more common chemical sedimentary rock is chert, which is composed of very finely crystalline quartz. Chert comes in many different colors and is one of the variety, was frequently used by humans for arrowheads, spear points, scrapers, and other tools chipped to hold a fine edge. Chert typically forms in two varieties. Bedded chert occurs as sedimentary beds or layers. Nodular chert is found as irregularly shaped lumps called nodules within other sedimentary rocks. Microscopic examination of bedded chert often shows that it contains the remains of tiny marine organisms whose skeletons are composed of silica rather than calcium carbonate. The organisms extract silica from seawater to form their skeletons and accumulate in layers on the seafloor when they die, eventually forming bedded chert. In other cases, silica-rich volcanic ash from a distant eruption can settle onto the sea surface and slowly sink to the bottom to become a layer of silica-rich mud that subsequently lithifies to become chert. In contrast to bedded chert made from siliceous fossils or silica-rich volcanic ash, nodular chert forms when silica-rich groundwater soaks through limestone and locally replaces it to form the nodules. Bioclastic sedimentary rocks. Carbonate rocks are primarily made up of the carbonate minerals calcite and dolomite, described in Chapter 2. Calcite-rich rocks are called limestone, whereas rocks rich in dolomite simply are called dolomite. Dissolved calcium ions are released into water during the chemical weathering of calcium-bearing rocks. The carbonate anion forms when atmospheric carbon dioxide gas dissolves in water. Seawater contains large quantities of both dissolved calcium and carbon dioxide. Clams, snails, corals, some types of algae, and a variety of other marine organisms convert dissolved calcium and carbonate ions to shells and other hard body parts. When these organisms die, waves and ocean currents break the shells into fragments that can range in size from boulders, in the case of some large corals, to clay-sized particles, in the case of certain types of algae that secrete calcium carbonate. A rock formed by lithification of such sediment is called bioclastic limestone, indicating that it forms by both biological and clastic processes. All limestones are calcareous, meaning they contain an abundance of the mineral calcite or aragonite. In many cases, the calcite mineral grains are too small to identify with the unaided eye or a hand lens, so field and laboratory geologists typically apply a small drop of dilute acid to the surface of a rock to see whether it is calcareous or not. If the rock is calcareous, the drop of acid will fizz, or effervesce, as it rapidly reacts with the calcite in the rock to produce carbon dioxide gas, the fizzing. If the drop of acid does not react, the rock lacks much calcite. Many limestones are bioclastic, meaning they contain the skeletal debris from broken down shells and other marine organisms with hard body parts. In addition to bivalves and gastropods, many marine organisms produce a hard skeleton that breaks down upon the animal's death. These include corals, sea urchins, and calcareous red algae in addition to calcareous microfossils called foraminifera and several kinds of calcareous green algae. Coral colonies can be branching or massive, and when broken down, they result in chunks of the original colony. Individual foraminifera are sand-sized and usually the calcareous skeleton, called a test, remains whole after the individual's death. Some calcareous green algae will break down into individual segments, whereas other types will break down into microscopic needles of aragonite. The diversity and abundance of marine organisms with skeletal hard parts made of calcite and aragonite is remarkable and has provided paleontologists with much information about changes to the marine ecosystem through geologic time. Perhaps no paleoenvironment has undergone a better documented set of changes in ecology through time than that of the carbonate reef. A reef is a wave-resistant framework of carbonate rock formed from the intergrowth of carbonate-forming organisms. In today's shallow marine reefs, corals are common as, for example, in the Great Barrier Reef of Australia. In contrast, about 100 million years ago, a type of clam was the dominant reef-building organism, and about 350 million years ago, a class of organisms called echinoderms was the main reef-building organism. Some reef-building organisms of the geologic past have no modern surviving counterparts, including stromatoporoids and archaeocyathids, the main reef builders of the Devonian and Cambrian periods. Many limestone-forming environments occur in shallow water that is close to being saturated with calcium carbonate, so in addition to broken-down skeletal debris from organisms with calcareous hard parts. Limestones commonly contain sand-sized grains called ooids that form from the precipitation of aragonite and calcite on the surface of a sand or silt-sized grain. Cross-sections of ooids show a well-developed concentric internal structure resulting from the layer-by-layer precipitation of the carbonate minerals. Peloids, sand-sized internally structureless grains of carbonate mud, are another very common type of grain found in carbonate environments. Unlike ooids, which require agitation to roll the grain around, peloids form under more quiet water conditions. Although reefs and reef-building organisms produce large pieces of bioskeletal debris, ranging in size from silt to boulders, many limestones are much finer grained and the individual fossils are too small to see without a microscope. For example, chalk is a very fine-grained, soft, white bioclastic limestone made of the skeletons of planktonic nanofossils called coccolithophorids that float near the surface of the oceans and photosynthesize. When they die, their remains sink to the bottom and accumulate to form chalk. Most fine-grained limestones contain an abundance of carbonate mud, or micrite, that are formed in the depositional environment either through the breakdown of larger particles, such as some types of calcareous green algae, or through the slow breakdown of calcareous debris to mud-sized particles by a type of microscopic algae. Some carbonate mud is formed through direct precipitation of tiny aragonite needles directly from seawater, forming isolated areas of white, cloudy water called whitings. All of these components, skeletal debris, sand-sized carbonate grains that form in the environment, and carbonate mud, are common constituents of limestones, carbonate rocks, and global climate. Carbon dioxide is greenhouse gas that traps heat in the atmosphere. Limestone is a hard, solid rock. Although it may seem counterintuitive, limestone rock is formed largely from carbon dioxide gas. Atmospheric carbon dioxide dissolves in seawater and forms CO, which then combines with dissolved calcium to form limestone rock, so formation of limestone removes carbon dioxide from both the sea and the air. In Chapter 1, we mentioned briefly that Earth's outer shell is broken into several segments called tectonic plates. The plates float on the weak, plastic mantle below and glide across Earth, moving continents and oceans. You will learn in Chapter 6 that after a tectonic plate moves thousands of kilometers across Earth's surface, it eventually sinks deep into the mantle. In some instances, a sinking plate may carry limestone into the mantle, removing large amounts of carbon from Earth's surface and sequestering it in the deep mantle. In other cases, limestone on a sinking tectonic plate may become heated to the point that carbon is recycled back into the atmosphere as carbon dioxide is emitted during volcanic eruptions. In these ways, the greenhouse gas is cycled between surface limestone, deep mantle rocks, and the atmosphere. Thus, interactions among limestone, the carbon dioxide in the atmosphere, and the carbon dioxide dissolved in the oceans are important. Determinants of global climate. Physical sedimentary structures. Nearly all